what I'm here to tell you about today is the story of quantum dots, from the discovery to their applications today as a technology. But first, I'm going to tell you a little bit about myself. I was born in Paris, in France, and my father is Tunisian. My father comes from this country here. My mother comes from Paris. And as a child, my family moved back and forth between France and Tunisia and North Africa, back to France, back to Tunisia, back to France. Eventually, we went to the south of France, in Nice. And then at some point, when I was 10 years old, my parents decided to move all the way across the Atlantic to the middle of the United States, in West Lafayette, Indiana. My father was a mathematician. He was a university professor. And he got a job teaching at the university there. The name of the university is called Purdue University. You take the first U in Purdue and you replace with the letter E. In French, that's perdu. That means lost. So when I went from Paris to West Lafayette, Purdue, I was lost. I was lost because, well, this is me as a young kid here, in my travel from Paris to Tunis. And here I am in the airport in Paris before going to West Lafayette. And I didn't believe my mother when she said that in the US, people did not speak French. So I didn't learn English because I was just a kid. I didn't think that people didn't speak French, right? So when I got to West Lafayette, nobody spoke French. I was lost. So that feeling of being lost, kind of lost, because when I traveled back and forth between Paris and Tunis and Tunis, I also went from different cultures. The French culture, the North African culture in Tunisia, back to the French culture, and then the US culture. And I kept changing schools. And I was always a little lost, But when you're a kid, you have to be resilient, right? So you have to change, to adapt to your feelings. And one of the ways I adapted was by becoming a little introverted and not to care too much what other people thought, right? So I didn't care so much what people thought. And this feeling of not caring so much about what other people thought about me turned out to be pretty important for my career in science. Because what I ended up starting to do with quantum dots, nobody else was doing at the beginning. And I didn't care, because I thought it was really interesting. And to me, that was enough. I didn't need to have everybody else think that it was very interesting. I didn't need for everybody else to be working on it because I was self-contained, partly as a result of my growing up in all these places. So after growing up between West Lafayette and Paris, because we went back and forth between the two also, I ended up in Cambridge, going to college at Harvard University. Then I went back to the Midwest in Chicago for my graduate studies. Then I went back to the East Coast in New Jersey for Bell Labs. Then I went back to Cambridge to this other school in Cambridge, which is MIT. When I was a student at Harvard, you've all heard of Harvard, right? Who's heard of Harvard here? You've heard of Harvard University, right?
Everybody knows Harvard.
Yeah, you all know Harvard University. Well, when I was at Harvard, I had never heard of MIT as an undergraduate.
Really?
I didn't know that there was another university in Cambridge until I had to take an exam, the GRE, it's a national exam, and I had to take it at MIT, and I had to look it up. And I had to take the subway from Harvard to MIT, and I had never seen MIT before. That's the first time I heard about MIT. And now I've been at MIT for 35 years or so. Okay, so Harvard was where I started learning about chemistry. And in high school, I was pretty good at chemistry. I thought I knew, what I was doing. But when I came to Harvard, I was lost again. It was the East Coast, different group of students, and the first exam that I took at Harvard, it was in a big room, kind of like this, and I was intimidated, lost, and I flunked it.
Really?
I got an F on my first exam in chemistry.
Wow, that's really good.
The lowest grade in the class. It was 20 out of 100. Why? Because I looked at the exam and I recognized all the words. And I started to do the first question and I panicked. I got paralyzed. I stopped, I went to the second question, and I panicked and I got paralyzed. I went to the third question, I panicked, then I went all the way to the end, and I just had written a few things on each question, and there was a bird flying around.
Oh.
And I just looked at that bird thinking, what am I going to do now? I left the class, and then I got, the lowest grade. I went home a little later, and I thought that was the end of my career at Harvard. I thought I was going to have to leave Harvard. My parents, convinced me to stay. How did I change? Because after that, I didn't get Fs anymore. I got good grades. What it turned out is that I didn't know how to study. I didn't know how to study. And so between the first exam and the second exam, I learned to study for an exam. Studying for an exam isn't just about knowing the material. It's about being able to recall it and do the problems quickly. It's basically a speed exam, right? So I learned how to solve problems quickly just by practicing. And after that, everything was fine. Studying for an exam is different than doing research. Research is about solving problems that nobody else has solved before. It's much more creative than an exam. But if you want to do really good research, you also have to know how to study for exams, because studying for exams allows you to have the material that you need in your brain easily accessible, so that when you have something brand new that you've never seen before, you have material in your brain that can help you to figure it out. So these are two skills that are different, but you both need those skills. So after Harvard, I went to the University of Chicago, and at the University of Chicago, I first started to do theory. I was a theorist, pencil and paper, doing mathematics for a few years. I loved it, but I realized that it wasn't enough for me, that my brain wasn't wired in the right way to do really good theory. And I missed working with my hands to do experiments, to discover new things experimentally, discover the world with my touches, with my senses. And I became an experimentalist. I became an experimentalist studying very small molecules, molecules that are of interest for the interstellar medium in outer space, molecules that create stars, that are around planets. One of the molecules I studied was H3+, which is 3 protons and 2 electrons. It turns out to be a very important molecule in interstellar space. And I loved that. I loved the studying these molecules, the quantum mechanics part of it. But again, I felt like it wasn't quite enough. It wasn't enough for me because this field of molecular chemistry, the physical chemistry I was doing, was a pretty old field. There was a lot of new things to study, for sure. But it had already been going on for 30, 40, 50 years. And I had the opportunity to go to Bell Labs in New Jersey, studying with Louis Bruce, and I discovered there quantum dots. And what I really loved about what I discovered at Bell Labs was that it was a brand new material. Nobody had studied it before. Any questions we asked was a new question. Any answer we got by doing an experiment was a new answer. It was brand new. I didn't care that there wasn't a community, because I didn't grow up with a big community at any time, moving back and forth. So there was no community of people working on this. There was just Louis that had discovered the effect. And then it was brand new and I loved it. I fell in love with the field. So after Bell Labs, then I kept working on quantum dots and I went to become a professor at the Massachusetts Institute of Technology.
So Moonji, let me just summarize a little
Yes.
bit in Korean what
Yes.
you just told.
Yeah.
간단하게 있잖아요. 그러니까 문제가 본래 아버지가 튀니지아니에요. 북아프리카 튀니지고 어머니가 이제 프랑스 사람이에요. 그래서 파리에서 태어나서 아버지가 유명한 수학자예요. 유명한 수학자가 가지고 이제 퍼듀 유니버시티라고 인디애나주에 있는 퍼듀 유니버시티에 미국에서 자연대 공대로서 한 탑 10에 들어가는 굉장히 좋은 학교예요. 거기에 이제 교수로 가가지고 같이 이제 미국으로 한 거예요. 그러니까 아까 이야기했지만 거기 미국에서 당연히 프랑스 말을 다 할 줄 아는 줄 알았는데 가보니까 프랑스 말을 프렌치 하는 사람이 아무도 없었어. 영어밖에 못하는 거예요. 그래가지고 그러면서 또 프랑스에 다시 갔다가 왔다 갔다 하면서 많이 돌아다녔어요. 보시면 여러 군데 돌아다녔죠. 그러다 보니까 굉장히 문제가 좀 내성적이었어요. 인트로버트 내성적이었는데 그런 것들이 결국은 뭔가 자기가 나중에 양자점의 그런 것들을 합성법을 발견하고 이런 것들이 훨씬 결국에 도움이 됐다. 그런 것들이 왜냐하면 문제는 다른 사람이 자기 어떻게 생각하는지 신경 안 쓰고 자기 하고 싶은 걸 하는 그것들에 자기 성격이 오히려 과학자로서 세계적인 과학자가 되는 데 오히려 도움이 됐다는 거예요. 그러면서 이제 가서 이제 하버드 대학 갔었는데 아까 들으셨죠? 첫 시험 봤는데 That's the first time I heard the story. 첫 시험 봤는데 F 받았어. 그러니까 100점 만점에 20점도 못 받는 거야. 그러니까 완전히 패닉이 돼가지고 하버드 대학 갔는데 하버드가 지금 세계 최고 대학인데 갔는데 패닉이 됐는데 근데 나중에 보니까 시험 잘 보기 위해서는 다른 방법을 좀 깨우쳤다는 거예요. 그래서 여러분들 뭐 길게는 안 해주셔서 어떻게 시험 잘 봤는지 모르겠는데 어쨌든 시험 보는 방법 빨리 문제를 풀어야 돼요. 주어진 시간에 우리 여러분 잘하는 거죠, 그죠? 한국에서 잘하잖아, 그죠? 그래서 그걸 깨달으니까 훨씬 이제 그게 자기가 처음에 받은 게 끝으로 그 다음부터는 그런 일이 없었다는 거예요. 그러면서 이제 가서 이제 하버드 졸업하고 시카고 대학에 갔었어요. 시카고 대학에 가서 지도교수가 이제 아까 전에 이야기를 자세히 했지만 지도교수 2명이 있는데 하나는 이제 고분자 물리하는 거였어요. 그러다가 나중에 지도교수 일본계 지도교수님한테 또 뭔가니 세상에서 가장 작은 모레큘이 수소 있죠. 수소 알죠? 가장 수소가 3개로 구성된 H3 거기에서 1가 이온을 가지고 H3 플러스 된 그걸 가지고 했는데 그게 뭔가니 거기 소위 말해서 별에서 어떤 현상이 일어나고 있는데 아스트로케미스트리거든요. 별에서 나오는 현상들을 이렇게 하는데 굉장히 큰 도움이 됐어요. 그래서 그렇게 있다가 결국 뭔가 시카고 대학에서 박사학위를 받고 그리고 이제 일반적으로 박사학위 받고 나서 바로 교수가 되는 게 아니에요. 특히 화학과 같은 경우는 박사학위를 받고 박사 후 연구원이라 그래요. 연구원 생활을 한 보통 길게는 3년, 짧게는 1년 그러니까 하는데 모운지 바웬디는 굉장히 좋게도 이제 그 당시에서 가장 박사 후 연구원 최고로 치는 데가 벨랩이었어요. AT&T 벨랩. 전화기 회사 있죠. 이 당시만 해도 미국에 전화기 회사가 하나밖에 없었어요. 지금은 여러 개 생겼는데 그 벨랩에 사는 연구실에 가서 연구를 하게 됐어요. 거기서 처음으로 오늘 이제 메인 토픽은 양자점 연구를 하게 된 거예요. Okay, that's your turn.
Okay, so now let me tell you about quantum dots. Okay, so quantum dot, as Professor Hyung told us, is a nanoparticle. It's very small. It's so small that you can't see it with a light microscope. So in order to be able to see it, you have to use a different kind of microscope, an electron microscope. And this is one of my students here working with this electron microscope. And if you do the chemistry correctly, and you make good quantum dots, you can then see it in the microscope, in the electron microscope, and this is what they look like. And you've seen pictures like that from the previous talk. Okay, so it's a very small particle. It's nanometers in size. And what makes it special, the properties that I found really fascinating when I first started, was that the electrons in these particles show something called the quantum size effect that Professor Hyung described a little bit. So let me tell you what that words mean, the quantum size effect. Okay? And it's going to be perhaps confusing, because quantum mechanics, when you first learn it, and even now, it's mind-blowing. It really is mind-blowing. The properties of electrons, really tiny electrons, are really weird because of quantum mechanics. So let me show you an experiment that shows how weird they are. Okay? Part of quantum mechanics is that something which is a particle, like an electron, can also behave like a wave, like a water wave, like an ocean wave, or like a sound wave. It can be both at the same time. It can behave like a particle moving in a wire, or like a sound wave. And this experiment done in an electron microscope shows that. In this experiment, you have a tip up there called the source, and it spits out an electron, one at a time. One electron comes out, you wait a few seconds, another electron comes out. And that electron that comes out, it moves from the source to a detector here extremely fast before the other electron has come out. So there's only one electron that goes from the top to the bottom at any time. Then a second electron comes. In this electron microscope, there's this apparatus in there. This is actually a very tiny wire. It's about the size of a human hair, okay? And then two plates, and they're charged positively, negatively, so that the electron has to follow a path between the apparatus. And then it gets detected here by a camera. And when it hits the camera, you see a flash of light. That's the electron hitting the camera. And so if you think of the electron as a particle, you might think, and this is a very reasonable thing to think, that the electron, when it comes out, is going to choose to come maybe this way, or maybe it will choose to come that way. And so when we image on the plate here, we might see a blob of electrons here, and a blob of electrons here, and a shadow in the middle corresponding to this. Okay? That's what we might think if it's just a particle. Okay? Let's do the experiment and see what happens. Okay, so now this is the experiment here. And let's start the movie. Okay, so there's an electron coming out. There it is. We just saw it. Another one, right? So these are the electrons. One electron hitting the plate here after going through the apparatus. And it looks pretty random. Like there's no pattern, like I said, if it's a particle, we might expect to see a lot of electrons here, and a lot of electrons here, and a shadow in between. Right now, it's too sparse. There's not enough electrons for us to see any sort of pattern. The experimentalists here, the video is speeding up, just because we don't want to wait here 20 minutes to see the whole thing, right? So it's speeding up, and then if you look very carefully, you'll see a pattern appearing. Right? Let's see what pattern appears. There's the beginning of a pattern. But it's not two blobs, right? It's not a blob here and a blob here with a shadow in the middle. It's a set of stripes. Where do the stripes come from? This is weird, right? How does this apparatus end up creating stripes of electrons when you're taking one electron at a time inside the apparatus. How does one get stripes like that if you've got two potential paths? One way is if you have waves. For instance, if you have water waves, and there's a barrier here, let's say this is the ocean up here, and there's a couple slots where the wave can go through, and the waves come out in those two places, and the waves interact with themselves. You know, when you throw a stone in a lake, you see the wave come out, and maybe there's a tree or something, and the wave reflects from the tree, and you get this very complicated pattern of waves inside the lake. So the same thing happens here with these two holes. And if you look far away, you see a set of stripes, just like these stripes here. Okay? So what's happening in the experiment here is that that electron comes out as a particle from the tip, but then it becomes a wave, a huge wave. And that wave sees both paths at the same time. Just like that wave here comes in and goes through both holes at the same time. So that one electron, what we think of as a particle, that one electron goes to both paths at the same time. It doesn't choose one or the other, it goes through both. And we call that, it interferes with itself. This is called wave interference. It interferes with itself, and we see the stripes. This is quantum mechanics. The idea or the reality that a particle isn't just a particle, it can also be a wave. Okay, so I hope I convinced you that an electron can be a wave. And now Professor Hyung maybe can explain a little bit what I just said in Korean.
Better to stop here and could you go back to previous slide? 지금 이제 뭔가니 현대 물리학의 시작은 뭔가니 양자역학이에요. 퀀텀 메커닉스. 양자역학 들어보셨죠? 양자역학 다 들어보셨죠? 양자역학의 가장 중요한 그런 전제 원칙 중에 하나가 뭔가니 소위 말해서 웨이브 파티클 듀얼리티예요. 그러니까 전자가 입자의 성질과 파동의 성질을 동시에 가지고 있다는 거예요. 근데 그것들을 방금 문지가 설명했듯이 바로 이 실험으로 보여주고 있는 거예요. 그래서 뭔가 이런 장치를 마련해서 굉장히 조그만 데가 전자가 하나만 뽕뽕뽕 나오는 거예요. 전자가 하나가 뽕뽕 나가는 거예요. 나와가지고 완전 입자 같으면은 완전 전자가 입자의 성질만 가지고 있다면 어떻게 해요? 여기 일부러 이제 중간에 있잖아요. 중간에 이걸 서로 이렇게 밀치게 해가지고 전자가 요리도 갈 수 있고 요리도 갈 수 있는 거야. 그러면은 전자가 여기 디텍트해서 이렇게 우리가 보는 데서 보면은 입자 같으면은 소복하게 오른쪽에 요만큼, 왼쪽에 요만큼 오해 있어요, 그죠? 입자 같으면 그렇게 돼야죠. 그런데 아까 전에 문제가 보여줬듯이 쭉 하니까 어떻게 돼요? 스트라이프 생겼어요, 이렇게. 그렇죠? 그러니까 한쪽에 쏠려가지고 오른쪽에 요만큼 모여있고 왼쪽에 이렇게 모여있고 그렇게 파리클 같으면 그래야 돼요. 파리클 성질만해서 그래야 되는데 그게 아니고 전자가 뭔가 조금 전에 I think next slide you see that the water waves interference. Yeah, that's right. 우리가 뭔가 이게 파동을 가장 쉽게 설명해 뭔가 이게 물이에요. 물결. 문지가 이야기했던 물결이 있어요. 그러니까 여러분들 그게 연못에서 돌 딱 던지면 쫙 이렇게 동심 쫙 그려져요. 그게 파동이잖아요, 그죠? 파동인데 두 가지 이제 슬릿에서 파동이 쫙 나가지고 물이 이제 물 파동이 있는 거예요. 웨이브가 해가지고 결국 뭔가니 여기서 보여주는 건 똑같은 형식이 돼버렸지, 그죠? 요게 소위 말해서 두 가지 동시에 나오는 이 파가 서로 간섭 현상에서 이런 게 일어나는 거예요. 그래서 결국 뭔가니 전자 하나가 바로 뭔가니 입자의 성질을 가지고 있을 뿐만 아니라 바로 뭔가니 파동의 성질을 가지고 있다는 걸 정확히 이 실험에서 지금 보여주고 있는 거예요. 이해가 이제 되세요? 그래서 전자가 이제 그거 가지고 이제 그 다음번에 Why don't you go ahead to the next slide?
Okay, well, first, I hope you agree with me that this is just mind-blowing, right? That a one electron can go down two paths at the same time. That's just mind blowing. Okay, and you have to accept it because clearly that experiment shows it. And so now let's go back to quantum dots. Okay, now we have this electron which we think of as a particle when it moves in a wire. We take that electron and then we put it in a nanobox. When we put it in a tiny box, that electron, it no longer behaves like a particle. It no longer behaves like it's running around the box. Instead, it's like in the apparatus that we just saw. It's the wave. It fills the entire box. Okay? That electron fills the entire box as a wave. It's not running around the box, it's just there as a wave. And our box, our nanobox, are these quantum dots, are these particles. So these particles are made up of many atoms. And we have one electron in there, and the box serves like a cavity for the wave. Okay? Now we know about sound waves and cavities. For instance, if I take a flute and a piccolo, I know that the flute has a lower pitch than the piccolo. That's because the cavity of the flute is bigger than the cavity of the piccolo, and the sound wave in the flute is longer than the sound wave in the piccolo, and that changes the pitch. We know the same thing for organ pipes. If you look at the big, tall, wide organ pipes, those are big cavities. They have big waves. The middle ones have smaller waves, and the smallest ones have the shortest waves. And so we associate pitch for sound with the size of the wave, right? The size of the cavity. It's the same thing for the electron in the box, for the electron in the quantum dot. The quantum dot is the cavity, and the electron wave changes depending on the size of the cavity.
Moonji, why don't you go ahead to the next slide?
Okay.
The quantum dot. Yeah. And after you finish this, I will explain to them.
Okay, all right. So what we're able to do with quantum dots is make different sizes, make different cavities for the electron. But we have to put an electron in here first. How do we put an electron in here? The way we do that is by providing energy. And we provide energy through light. We shine blue light, that's energy, and this quantum dot is full of atoms and it's full of electrons, but all these electrons are right next to atoms. They're not free to go and become waves. But by putting energy in there, we can take one of the electrons that's next to an atom, we liberate it, we allow it to become a wave to fill the cavity. Okay? Eventually, that electron, that wave that's been liberated, comes back to where it belongs and releases the energy as light. It releases the energy as light, and depending on the size of the cavity, you then have different color light. And this is kind of like the pitch of the sound wave, right? So big cavity has a lower pitch, small cavity is a higher pitch, which corresponds to color instead of sound.
So could you go back to the previous slide? Go back to the previous slide. Yeah, one more back. Yeah. 이제 여러분들이 아까 전에 이제 전자가 굉장히 작은 걸 입자잖아요. 이것들이 입자의 성질을 가지고 있을 뿐만 아니라 파동의 성질을 가지고 있다고 조금 전에 이제 설명을 잘했잖아요. 제가 이제 보충 설명을 좀 했고요. 그렇잖아요. 근데 실제로 문지가 이야기하는데 문지가 아까 전에 바이올린 들고 있었잖아. 바이올린도 킬 줄 알고 그 다음번 문지가 이 위에 있는 이게 flute, you can play flute, right? 플루트 플레이 하는 거예요. 여러분 박수 한번 주세요. 플루트 할 수 있어요. 자, 근데 보면은 피콜로라고 굉장히 작은 악기가 있잖아, 그지? 여러분 알잖아, 피콜로라고 굉장히 작은 악기야. 피리 비슷한 건 작은 악기인데 이거는 플룻은 길잖아. 그러니까 사운드가 나오는 게 다르지, 그지? 피콜로는 굉장히 센 피치로 나오고 플룻 같은 건 조금 더 중후하게 나오잖아, 그지? 여러분들 바이올린 같은 경우는 굉장히 좀 이렇게 그리고 첼로 하면 무게 우 이렇게 첼로 사운드 나오죠, 그죠? 사이즈가 다르잖아. 그러니까 이게 뭐예요? 여러분들 듣는 음이 다르잖아. 결국 아까 전에 제가 입자가 파라 이야기했지. 입자, 그러니까 전자가 입자의 성질을 가지고 있으면 뭐야? 파의 성질을 가지고 있는 거야. Next slide. 예. 이제 보면은 여러분 이제 대성당 같은 데 보면은 큰 교회나 성당 같은 거 보면은 이게 파이프 오르간 했잖아. 파이프 오르간이 이제 정확히 보여주거든요. 파이프 오르간 보면은 이게 파이프 오르간의 실제로 길이에 따라서 어떤 것들이 소리가 이제 달라지는 거예요. 그죠? 자, 그것들을 next slide. 보면은 실제로 굉장히 나노미터 사이즈로 퀀텀닷이 뭔가니 반도체를 나노입자를 제가 아까 말씀드렸지만 문제도 이야기했지만은 반도체를 나노입자 상태로 만든 거야. 거기에 나노입자 나노미터 사이에 거기다가 전자를 가두어둔 거야. 본래는 전자는 뭔가에 꼭 묶여 있어. 묶여 있는데 전자 하나로 뽕 자유롭게 또 만들려고 거기다가 에너지를 그때 전기를 가하거나 안 그러면 외부에서 에너지가 또 빛을 강한 빛 이게 일반적으로 여러분 빨주노초 반환보 아시죠? 그죠? 그러니까 보라색으로 갈수록 에너지가 더 높은 거 알죠? 그죠? 그러니까 레드가 에너지가 가장 붉은빛의 에너지가 가장 작잖아. 무지개색 중에서. 그지? 그다음번에 그거보다 어쨌든 블루 라이트 같은 거나 이런 것들 딱 조여지게 되면 뭔가 전자가 하나 뿅 자유롭게 되는 거야. 자유롭게 되는데 이놈은 이제 마음대로 움직일 수 없어. 여러분들 있잖아. 꽉 갇혀 있으면 마음대로 뭐 돌아다니지 못하잖아. 그러니까 이게 뭔가니 어떻게 되는 거? 그 갇혀 있는 공간 내에서만 파동으로 움직이는 거야. 아까 전에 제가 피콜로하고 거기 플룻하고 이렇게 비교했듯이 사이즈에 따라서 갇혀 있는 공간의 크기에 따라서 이게 사운드가 달라지잖아. 다른 말로 표현하면 뭔가니 아까 제가 발표할 때 얘기했지만 전자가 하나 빛을 조여주거나 전기를 조여주거나 쫙 위로 올라갔다가 다시 원상 복귀하는 거야. 그런 에너지 차이가 밴드깁 에너지를 이야기했지. 그죠? 그 에너지 차이가 빛으로 나오는 거야. 그게 바로 형광이야. 근데 빛은 뭐야? 빛은 파장이지. 그지? 파장, 색깔 그것들은 결국 뭘로 결정되겠어? 결국 뭔가 얼만큼 높은 데서 떨어지냐에 따라 결정되지. 아까 전에 피콜로하고 플루다. 그래서 보세요. 사이즈가 달라지면은 나오는 색깔이 좀 크게 만들면 빨간색, 좀 더 작게 만들면 초록색, 그리고 여기서 안 보여주는데 훨씬 더 작게 만들면 파란색까지 이제 나올 수가 있는 거야. 이제 이해가 되셨어요? 어떻게 해서 색깔들이 퀀텀닷의 입자 사이즈가 점점 더 작아지면은 점점 더 높은 에너지의 빛이 나오는지를 이제 이해하시겠어요? 그것들을 지금 써요. 오케이, next yours.
Okay, so today, as you've heard from Professor Hyun, quantum dots are used in displays, and I'm sure there's some display around in this building that has quantum dots in it. They're made in huge quantities, and they provide the colors in many sorts of displays. They're used in biology, they're used in energy applications, and all sorts of things. But 40 years ago, more than 40 years ago, they didn't exist. The effect hadn't been discovered yet. And 40 years ago is when Lou Bruce and Alexei Ekimov discovered the effect of quantum confinement. The idea that a piece of semiconductor, if it's small enough, acts like a cavity for a single electron. The way they came about to their discovery, which was part of the Nobel Prize for the discovery and synthesis of quantum dots, they're the discovery part. I'm the synthesis part. Okay? Alexei Ekimov, he wasn't interested in making better displays. He didn't know anything about displays. In fact, LCD displays didn't exist really in 1982. OLED displays certainly didn't exist in 1982. He was interested in stained glass windows. He was interested in the color of stained glass windows. What made the color? And we already knew that the red color in stained glass windows was due to very small nanometer-sized particles of gold. If you take gold and you shrink it down to a small particle, it doesn't look yellow anymore, it looks red. It's very stable, and that was known already by Faraday in the 19th century. And he was interested in what makes the other colors. And it's that interest in the colors of stained glass windows that allowed him to take glass with a few elements, to melt it in different ways, and to find that depending on how he melted the glass and let it cool, with the same elements in the glass, he would see different colors. And he wondered, why is that? And so he did an experiment with an X-ray machine to find out the size of the particles. It's called small angle X-ray diffraction. So using that technology, he could then correlate the size of the particles he was making in the glass with the color that he was seeing. And he realized that this was this quantum effect, that he was seeing these electron waves in these particles. And he wrote a paper in 1981 in Russian, because this was the Soviet Union at the time. And the first three words are quantum size effect, the cavity effect of the particles and the electron wave in that. This was written in Russian. At the time, in 1981, it was the Soviet Union, and there was very little connection between the Soviet Union and the Western world. Soviet journals were not being translated, or if they were, it was very slow. And so that knowledge stayed in the Soviet Union. Lou Bruce was working in the US at Bell Labs. What he was interested in, again, it wasn't making better displays. What he was interested in was to understand how fast electrons go from inside a semiconductor to a solution where you might use that electron to do chemistry, perhaps to make a fuel from sunlight, like hydrogen, something we're interested in today also, something called photocatalysis. And in order to study the speed at which electrons go from the semiconductor to the solution, he used something called a picosecond laser to sort of time gate the process of the electron moving across. And to get better signal, he needed more surface because it's going through a surface. You get more surface by making the particles smaller and smaller so that the surface to volume ratio becomes large. So he took his particles and made them smaller and smaller and smaller to do this experiment. And at some point, he started seeing that the colors changed. Every time he did the experiments and made a sample, he got a different color. And at first, he thought maybe he was a bad experimentalist. You know, he wasn't using the right chemicals or something. But then he realized that what he was seeing was this quantum effect. And at Bell Labs, he had electron microscopes, like the one I showed you at the beginning, and he was able then to correlate the color he was seeing with the size of the particle. And he wrote a paper in 1983 in the Western literature with the first three words, quantum size effect, the same three words as Ekimov's. This is written in English. It wasn't until many years later that the two realized that they were working essentially on the same thing. Want to translate or?
I think this is better summarized. So, 보면은 이제 그 당시에도 있잖아요. 81년도였거든요. 항상 여러분 이제 노벨상은 가장 중요한 게 누가 최고 먼저 했느냐예요. 그런데 그 당시에도 먼저 소련에서 에키모프 박사님이 최고 오른쪽에 계신 분인데 에키모프 박사님이 소련에서 연구를 하고 있었는데 여러분 보면 이제 그 유럽에 가면은 큰 성당에 유리창을 보면은 유리창이 스탠드 글라스 보면은 그게 여러분 앉아 있는 의자 색깔 비슷해. 포도주 색깔이거든, 그죠? 그게 뭔가 아니에요. 금을 유리에다가 집어넣어 가지고 가열하게 되면은 유리를 만들 때 금을 좀 집어넣으면은 색깔이 그렇게 포도 색깔이 바뀌는 거예요. 그건 이미 잘 알려져 있었어요. 근데 마이클 파라데이라고 유명한 그런 영국의 과학자가 이미 1890년 정도에 이렇게 이미 알려진 거예요. 그래서 이 사람들이 관심 있는 게 항상 있잖아요. 과학자들은 이게 QLED 될 거다가 연구를 시작하는 게 아니에요. 처음에는 항상 호기심을 시작하는 거예요. 그래서 뭔가니 다른 엘리먼트도 혹시 비슷한 스탠드 글라스 비슷한 현상이 일어나지 않을까 여러 개를 집어넣어 본 거야. 근데 에키모 박사님이 커퍼 클로라이드라는 물질을 집어넣어 해보니까 색깔이 나오는 거야. 근데 컨디션에 따라서 색깔이 바뀌어. 근데 그 현상을 이제 소비에트 저널에다가 그러니까 그 당시에는 러시아는 아니고 소비에트 유니언이니까 그 저널에다가 81년 논문을 발표했어요. 그 당시에는 미국과 소련 간에는 서로 교류가 없었어. 아무것도 모르고 루브루스 박사님은 뭔가 똑같은 비슷한 연구를 한 거야. AT&T 벨랩에서. 그래서 여기 논문 타이틀이 똑같잖아요, 그죠? 퀀텀 사이즈 이펙트. 퀀텀 사이즈 이펙트. 비슷한 연구 결과를 뭔가 물질은 약간 다른데 입자가 사이즈가 이렇게 바뀌니까 이게 뭐가 색깔이 바뀌더라. 그 논문을 이제 저널 오브 케미컬 피직스라는 미국 저널에다가 미국 논문을 발표한 거예요. 오케이.
Okay, so this was 1981 to 1983. Where I come in is after spending some time at Bell Labs as a postdoc, I went to MIT to study quantum dots, to study the physics of quantum dots. And I needed to make samples to study the physics. My interest, my curiosity, because, he was curious about stained glass windows, and he was curious about how fast electrons go from semiconductors to the liquid. I was curious about how the properties of a big piece of semiconductor come about from atoms. If you look at an atom, its properties are completely different than the properties of a piece of semiconductor like the one you have in your computer. And as you add atoms together one at a time and you make a bigger and bigger particle, at some point, those properties of this ensemble of atoms are going to start to look like the big piece of bulk, big piece of semiconductor. And then my curiosity was, how does that happen? How does the properties evolve in this small size regime? In order to study that, I need to have really good samples. And I spent my first 3 years at MIT trying to make this good sample. And it was 3 years full of failures at the beginning. Nothing worked, and eventually we got it to work. And we wrote a paper, this 1993 paper, with my students Chris Murray and David Norris, which was then the synthesis part of the Nobel Prize. There's Chris here, and there's David here as young men. They're not so young anymore. They have white hair, just like I have white hair. And what I realized that we needed in order to make really good particles where they're all the same size, basically in solution, with very good crystallinity, we needed 3 things. We needed high temperature. In order for the atoms in the crystal to be exactly where they need to be, they need to have enough energy to move around and find their place. That's provided by the heat. We needed to separate out the nucleation step from making little tiny seeds and the growth step, because it was known from the 1950s in physical chemistry that if you could separate out nucleation and growth, for bigger crystals, you could make something that had a good size distribution where the end product was pretty homogeneous. This idea of nucleation and growth is something that you already know about if you've seen snowflakes. Every snowflake is different, but when it's wet and humid out and close to the freezing point, what happens at the snowflakes, they nucleate as tiny seeds in the clouds. They come through the atmosphere, and then water molecules come and aggregate on the snowflake. And when they come to the ground, they're all big and fluffy. They're all roughly the same size. If it's really dry and really cold out, you make tiny seeds in the clouds. Those seeds come through the atmosphere. There's not too much water. And by the time they get to the ground, they're also all the same size, but they're all tiny. Nucleation in the clouds, growth through the atmosphere, and you get at the end product objects that are roughly all the same size. So the idea of separating nucleation and growth was something that was, pretty obvious to try to do. The third thing we needed was we couldn't have any water or oxygen, because these semiconductor materials, in the presence of oxygen and water, for instance, cadmium selenide, if you have oxygen around, they don't stay as cadmium selenide, they become cadmium oxide. They react with the oxygen very easily. So we had to get rid of oxygen and water. And this is what we created because I wasn't really a chemist, you know. I was a theorist first. Then I was a small molecule chemist thinking about molecules in space, right? And then suddenly I'm trying to do chemistry, and I had no idea what I was doing, but I had some ideas of what I wanted to happen, right? But it had to be simple, because I wasn't going to make complicated molecules. So we used metal organic precursors. These are molecules that contain the elements that we need for making the semiconductor. They're stable at room temperature. Then we have our solution here that's hot, 300 Celsius. When you take these molecules and inject them rapidly in the hot solution, they fall apart because they're no longer stable at high temperature. They release the elements, and these elements react together to form the little seeds, just like the seeds of ice in the clouds. And then there's enough elements going around that they begin to grow together on the seeds, just like the seeds of ice from the clouds coming through the atmosphere, aggregating more and more water molecules from the snowflakes. And so by controlling the conditions here, we could have the rapid injection, the nucleation, and the slow growth without air. This is under nitrogen, right? And that's how we created our particles.
이제 노벨상을 받게 된 게 뭔가 하니 실제로 아까 전에 이제 81년, 83년 논문 이야기했잖아요, 그죠? 그래서 처음으로 아까 전에 제가 이야기했지만은 이제 저도 이야기했고 문지가 발표할 때 이야기했지만은 입자 크기가 바뀌게 되면은 형광 빛깔이 바뀐다. 여러분 몇 번에 이미 들으셨죠, 그죠? 그 현상을 처음으로 발견한 사람이 에키메프 81년 소련 논문, 그 다음번에 83년 루브르스 논문이에요. 근데 문지 바웬디 교수가 노벨상을 23년에 받게 된 게 뭔가니 실제로 그것들을 제대로 된 나노 입자를 균이랑 똑같은 그 균이랑 나노 입자를 합성하는 기술을 개발한 거예요. 그래서 보면은 문지 백그라운드 본인이 이제 인정하듯이 합성 화학자가 아니야. 이론에 가까운 그런 물리화학이라는 분야를 전공한 사람인데 MIT 교수대가 처음에서 새로운 분야를 뛰어드니까 굉장히 힘들었잖아요. 그래서 3년 동안 굉장히 고생을 많이 한 거예요. 근데 다행스럽게 이 똑똑한 대학원생들이 있었던 거예요. 크리스 모리하고 데이비드 노리스라는 똑똑한 친구가 지금은 교수하고 있어요. 에테아 교수를 하고 있고 유펜의 교수를 하고 있지만 이 친구들이 굉장히 똑똑하게 이제 같이 한 게 된 게 뭔가 하니 자 문제가 이제 처음에 하는 양자점이 뭔가 하니 반도체가 CD, 카드뮴, 셀레나야 되는 거예요. 여러분 이제 주기율표 보면은 옥시전이 산소가 최고 위에 있고 그 다음번에 설퍼, 황이 있고 셀레늄 SE가 있거든요. 이 말은 무슨 말이에요? 산소가 워낙에 반응성이 좋기 때문에 그냥 셀레늄 같은 거 그냥 금방 산소로 바뀌어요. 산소가 조금만 있으면. 그래서 문제가 생각한 게 절대로 공기가 들어가서 안 된다. 두 번째 뭔가는 이제 아까 조금 어려운 현상인데 여러분들 있잖아요. 완전히 공기 중에 먼지가 하나도 없으면 비가 안 와요. 먼지가 하나도 없고 진짜 100% 순도의 공기 같으면 비가 절대로 안 와요. 왜냐하면 핵이 형성이 안 되거든. 그래서 모든 빗방울도 그렇고 아까 전에 문지가 이야기했듯이 거기에 눈이 내리는 것도 마찬가지고 그런 입자거든. 입자가 형성되려면 첫 번째 핵이 형성되고 뉴클리에이션 핵이 형성되고 그 다음번에 핵이 형성되고 그것들이 내려오면서 주위에 있는 습기가 들어가서 해서 물방울이 돼서 뚝뚝 떨어지는 거예요. 아시겠어요? 그런데 중요한 게 뭔가니 균일하게 만들려면 뭔가니 핵 형성되는 것하고 성장하는 것을 분리를 해놔야 돼요. 왜냐하면 핵이 여기서 생기고 한 또 몇 10초 있다가 생기고 100초 있다가 생기고 그러면 똑같은 그게 속도로 성장한다 생각하면 돼요. 처음에 생긴 게 입자 사이즈로 클 거고 나중에 생긴 게 조그맣죠, 그죠? 그러면 균일한 사이즈가 안 나오죠. 그러니까 문제가 얘기했듯이 핵이 형성되는 거하고 완전히 분리돼 가지고 성장해야 되는 거야. 그렇게 한 기술들을 구현해 가지고 실제로 아까 보여드렸듯이 균일한 나노 입자를 만들었다는 거야. 근데 이 모티베이션의 전체는 뭔가 아니에요. 어떻게 하면은 우리가 이제 구리 예를 들면 구리는 전기 잘 통하잖아요, 그죠? 근데 구리 원자 한 개가 전기 통할까요, 안 통할까요? 안 통해. 그러면은 구리 원자를 몇 개나 모으면은 정말 구리가 구리답게 전기를 통할까? 그게 관심이 있었던 거야. 그러려면 어떻게 됐어요? 굉장히 제대로 사이즈 크기가 균일하면서 사이즈가 바뀌는 그런 것들을 반도체를 합성할 수 있다. 그것들을 실제로 처음으로 보여준 거예요.
Okay, and there's a video. So there's the syringe here that contains the precursors. This is at 300 Celsius. And there's the quick injection, like an injection in your arm, let's say. And then the change of color. Those are the seeds. Those are the seeds. And then we have a slow growth. And I'm going to skip some of the video here because we don't want to wait 20 minutes. And it's slowly growing, the color changes, and now it's much darker. So it's that lower pitch, it's a big organ pipe now. It's the flute instead of the piccolo, right? The wave is bigger, and you see the colors of the different vials as he's taking samples out, going from yellow to red. And then what he's going to do, he's going to shine blue light on the samples, and we're going to see then the release of the energy from the small particles to the big particles, as you see here. Okay? And so then, I started in 1990 as an assistant professor, and it took us a while to figure this out. And I wanted them to be really good, these samples. And I had to have patience. Although I had many nights where I couldn't sleep very well because things weren't working so well at the beginning, and I didn't think I was going to survive as a professor. I thought my career was going to end. If you have a professor starting out and they don't write any papers for 3 years, their colleagues then think that something is wrong with them. But, I didn't care because I didn't care, right? Because I was always lost and I didn't care. So we wrote this paper in 1993, and there's a few words that are underlined. It was simple. It was a single reaction, and we created something to purify the material. Why is that important? I didn't know it was important back then. It's important for making a commercial product because the cost of making anything is related to the number of steps you need to make it. If you have a drug molecule, a complicated drug molecule, it's expensive to make that drug molecule. You have a computer chip that has a lot of complications in it, like a chip from NVIDIA, let's say. Very expensive to make because there are many steps to making it. Simple and one step meant that it was going to be very inexpensive to make. And then we could purify it, which means that we could then use it like a big molecule and incorporate it into other materials like liquid molecules.
실제로 이제 거기 미국에서 교수가 이제 처음에 조교수로 들어오잖아요. 그러면은 한 5, 6년간 열심히 연구를 해가지고 그걸 기준으로 해서 이제 텐녀, 정년 부장을 받는 거거든. 그러면 이제 그 다음부터는 나쁜 짓 안 하고는 거의 학교에서 쫓아내지 못해요. 근데 3년 동안 논문이 한 편도 없어. 3년 동안 논문이 한 편도 없는 거야. 그러니까 얼마나 스트레스 받았어. 그래서 잠도 못 자고 계속 잠도 못 자고 스트레스 받은 거야. 지금은 이제 웃으면서 이야기하지만 엄청난 스트레스 많이 받은 거야. 그랬었는데 실제로 이제 그 크리스 모리 대학원생들하고 같이 열심히 해가지고 실제로 이 논문이 바로 노벨 프라이즈 위닝 페이퍼예요. 이 논문이 노벨 프라이즈 위닝 페이퍼거든요. 근데 문제가 강조한 게 뭔가 아니 여기서 어떤 것들이 실제로 결국은 그것들이 아까 이야기했지만 삼성 QLED 텔레비전으로 연결이 됐잖아요. 조금 이따가 문제가 자세히 이야기하겠지만 근데 그렇게 하기 위해서는 몇 가지 키워드가 있는데 이게 너무 있잖아요. 뭐든지 여러 스텝을 거쳐가지고 복잡하면은 값이 비싸지잖아. 근데 이 프로세스는 그냥 싱글 프로세스야. 한 번밖에 안 해. 단일 공정이니까 굉장히 간단하잖아. 그러니까 이것이 실제로 삼성 QLED를 만드는 그런 것들이 가능하게 싸게 할 수 있으니까 간단하고, 그 다음번에 여기 사이즈 셀렉션 프레시피테이션, 아까 전에 제가 제 발표 때 이야기했죠. 그러니까 처음에는 완전히 균일하게 안 나오니까 이 방법을 문지가 개발해가지고 완전하게 똑같은 크기로 만들 수 있는, 똑같은 유니폼하게 하는 반도체 난입자를 합성하는 것들을 개발하고, 그것들이 결국 뭔가니 노벨 프라이즈를 받게 된 논문이 된 거예요.
Okay, so lost my train of thought here. So I know that he said some things that I didn't say.
I know, but that's not bad. Don't worry about
But that's okay, because I understood what he said, even though it was in Korean. So that was our paper. And then we started to study the physics of it, right? And I want to remind you of the time scale. The discovery was 1981. It took more than 10 years for really good material to be made, right? 10 years, 1993. But things started to speed up after that. After we had good material, then a community started to appear. At the beginning, it was Lou Bruce, it was me, it was Paul Rosados at Berkeley, and that was pretty much it, and our students. But once we had shown that we could make material that you could actually study and make reproducibly, a lot more people became interested in these nanomaterials, including Professor Hyung here. The next important advance, so when we first made the material, they didn't emit light very efficiently. The efficiency was about 20%. So about 20% of the energy came out as light from the energy that you put in. I thought it was really amazing because before my synthesis, the efficiency was 0%. And 20% is infinitely bigger than 0%. I thought they were incredibly bright. But one of my colleagues in Germany reminded me that he said, 20% means that 80% of your sample is worthless. And so, yeah. And so as a community, then, we tried to do better, to make it 100% efficiency. And the way that happened is by making these more complicated particles called core shell, where we have the quantum dot inside, then we surround it by another semiconductor, and then we have all the organic groups around here. This is like an M&M. The story about M&Ms is they melt in your mouth, not in your hand, right? So this is like the shell of the M&M. It protects the quantum dots, so it doesn't interact with the surroundings. And so creating these structures allowed for the efficiency of the light to come out to become 100%, as good as it can be. And then you saw these beautiful colors, very bright colors that the eye can see. So this happened in 1996, 1997, 3 years after we published our paper. 1998, and so we create the colors by exciting with blue light, like I showed before. 1998 was the first company, Quantum Dot Corporation, where as chemists, what we knew best was biology. We thought we can use these things in biology because they emit light. When you shine blue light on them, we can use them to label the inside of cells and to use different colors to label different parts of the cell and to study the cells this way. So the company, Quantum Dot Corporation, I was a co-founder along with Paul Rosados and Shimon Weiss. And this is a picture from a paper from the company where this red are quantum dots and the green are dye molecules that were also being used then. What you see here is the function of time is the quantum dots stay stable while the dye molecule, this organic dye, fades away. And this showed the stability of the dots was really great. And that was a selling point really for the dots. Many colors and really stable. You want to say anything? Yeah.
I just want a little bit.
Yeah,
그래서
you could
이제
go
실제로
faster.
이제 기술이 문제 가장 이제 중요한 게 모운지 바웬디 교수가 가장 중요한 게 뭔가요? 기술이 이제 그런 거 티클링 포인트거든요. 어떤 순간에 있잖아요. 굉장히 기술이 천천히 발전하다가 어떤 계기로서 팍 있는데 결국 그것들을 공헌한 게 문제가 이제 조금 전에 보면 노벨 프라이즈 위닝 페이퍼가 그걸 제공한 거예요. 이제 제대로 된 양자점을 퀀텀닷 합성할 수 있으면 그 다음부터는 사람들이 이제 만들어서 뭐 할 건가 응용을 계속 찾는 거예요. 근데 응용을 하려고 보니까 처음에 보니까 이제 이걸 LED로 이용하고 싶은데 LED 그러니까 효율이 20%밖에 안 나온 거야. 20%밖에 20%밖에 안 나오는 거야. 그래서 고민하다가 문관이 여러분 M&M 초콜릿 알죠, 그죠? 초콜릿 보면은 손에 있을 때 안 녹잖아. 근데 입에 넣으면 뭐예요? 녹죠, 그죠? 왜냐하면 M&M 초콜릿에 이렇게 코팅이 되어 있잖아. 그 비슷하게 프로텍션을 갖다 코팅을 하니까 결국 문관이 양자점의 수율이 확 올라가는 거야. 그것도 이제 좋은 논문인 거야. 그렇게 해서 첫 번째는 이것들은 이제 나중 삼성 QLED가 되지만 그 텔레비전을 응용하는 거 넥스트 슬라이드. 그 다음번에 이거 똑같이 뭐 다른 응용처를 여러 가지 찾는 거예요. 그래서 이제 우리가 생물학이나 이런 데서 결국 뭔가니 의료인데 중요한 게 뭔가니 셀에 있는 것들이 어떻게 움직이고 있는 것들 관찰하는 게 굉장히 중요하거든요. 근데 기존에 이제 유기물 베이스로 한 것 같은 경우는 보면은 시간이 지나면 다 없어졌죠, 그죠? 그런데 이 양자점은 무기물이잖아. 훨씬 안정한 거야. 그러니까 오랫동안 해도 그 빛이 그대로 딱 나오죠. 그러니까 오랫동안 관찰할 수 있고 훨씬 더 어드밴티지가 있어. 그래서 이제 다양한 응용 가능성을 막 하나 보여주고 그러면 이렇게 이제 합성만 제대로 되면 여러 군데서 일어나가지고 뭐 우리 연구실도 그렇고 막 해가지고 이 연구 저 연구 응용 가능성을 애플리케이션을 응용 가능성을 보여줄 수 있는 거예요.
Okay, so the stability turned out to be important later for the display applications where you needed the displays to last a long time without fading away. But we didn't know that at the time, right? So I became much more interested in putting the dots in vivo, in living animals to study the biology of living animals and doing complicated experiments like looking for these rare cells, like these are stem cell-like cells, and trying to image them and find them and using multicolors of quantum dots that only go to these cells. For instance, these red dots, we can inject red dots and green dots, and these rare cells that we're looking for can be labeled both by red and green dots, and red and green together, when it emits, that looks yellow. So you go with your microscope and you look for yellow, and that's that very rare cell, and then you can study that rare cell. So these are really complicated experiments that can teach you about biology. And this is all good, but this is not a very lucrative way of making money from quantum dots, because these are hard experiments, these are not humans, this is for research. The application that came now in the mid-2000s, actually the 2010 was the beginning, that was the easier application. And it was because we started talking to electrical engineers. So by talking to different communities, we started to understand the needs of different technologies, right? And so there were two companies that were started in the early 2000s, Nanosys and QD Vision, and I had something to do with both of them, and both of them are part of bigger companies now. And the first product that came out from QD Vision was this LED light bulb in 2010. When these LED light bulbs first came out in 2010, they were too blue. The light that came out didn't have enough red in it. And so if you were to, say, use them in your bathroom, and you looked at yourself in the mirror in the morning, you would want to go straight back to bed because you would look like a ghost. Because the mirror, you wouldn't see any of the red from the blood in your face, right? And so the way to fix that was to take some red-emitting quantum dots in a plate there. They would absorb a little bit of the blue, they'd get excited and re-emit red light, and then we would have all the colors that were needed for the eye to see that you are actually healthy, right? That was a product that you could buy for a few years, and that was fine as a product for as long as these light bulbs cost $100. I don't know what $100 is in Korean currency, but it's a lot of money. Soon, these light bulbs became much cheaper. And when they became like $20, you couldn't make any money anymore by putting dots on top. And they had other ways to make than the red color from the LEDs. But QD Vision realized they had to shift, right? They had to find another product. And they realized that the same technology of taking some of the blue light, making it into red light, could be used in displays. In LCD televisions, if you could use a blue LED here to provide the light, have quantum dots in a glass rod. This is a glass rod filled with quantum dots in polymer that can emit red or green light. Then some of the blue gets absorbed here and excites the electron. Then you get blue, red, and green light in the back of the television. And that's all the colors you need to make a color television. And that turned out to be a really good idea. But we didn't know that back in 1998 when we started Quantum Dot Corporation, and we didn't even know that when we started Nanosys or QD Vision in 2005. It wasn't until 2012 that this television came out from Sony first, using cadmium-containing quantum dots from QD Vision. And they were pretty good television. I still have two of them, Sony didn't give me one. I asked them to give me a television because, it was my dots in there. They said, well, you're going to have to buy them, right? So I had to wait a year, 2013, when they became on sale, cheaper, and I ordered them from Amazon. That's how I got my first quantum dot television. And it took 3 tries. The one I got from my office was huge, 65 inches. The first TV came, and the screen was cracked, so I had to return it. The second TV came, and the screen was cracked. So it turned out that Sony didn't understand how to package their televisions. They had cardboard, then the glass screen, and nothing in between, and it would just crack. Maybe that's why they stopped making it. No, they stopped making it because of the cadmium, actually. Samsung saw this and saw, this is a great idea, but we don't want to put cadmium in our televisions. So instead, they put this indium phosphide and created this QLED television, and which Professor Hyung talked about. So that was in 2015, about 20 years after the synthesis, right? So we have 1980, 10 years, not much happens, the synthesis. Then a lot happens in terms of the science. Well, we have to wait another 20 years for this technology to appear. And that's become very successful. And today it's a combination of OLED, it's QD, it's a combination of OLEDs, it's pixelated OLEDs with quantum dots inkjet printed. And you can make very large, very bright televisions with beautiful colors. And they're all over Korea. You go to the airport in Incheon, and it's full of QD OLED TVs, and it says that, on it. So that was the big commercial success. There are other applications. For instance, now people are trying to make light directly from the dots without going through the blue light by putting electricity directly in the dots and making, like we showed, flexible light-emitting displays. There are applications in putting light in and getting current out, which is what you need for making solar cell to create energy. This is me with some solar cells as sunglasses here, and also for reading infrared light. So there are companies that are trying to make that. So there are many more applications that are coming about. You want to? Okay. Okay, so it took a lot of students to go through this. I've had about 150 students, and this is a list of them, and I'm really grateful to all the students because they're the ones that do all the hard work, And now I sit in my office and I tell them what to do, and they usually ignore me and they do whatever they want, and it's usually much better than what I told them to do anyway. So it makes me this is why I stay what I do, because I have great students. I get to talk to amazing colleagues and learn about all sorts of things like biology and medicine and electrical engineering, and it's just wonderful to be what I'm doing. I'm going to leave you with a few bullets that I was asked to put together about a year ago when I gave a talk. And what advice, like Professor Hyun had, work hard, work together, something, and eat and enjoy life. So I have enjoyed life also, right at the bottom. So my points are, stay curious, right? Stay curious about everything. Not about just the world around you, but when we do an experiment, we want to be curious about how the experiment works, because that teaches us what we might do better. Keep learning, because if you're curious, you're going to keep learning about all sorts of things, and they're going to give you ideas to pursue, maybe to discover new things by keeping on learning. But as you try to do your research or try to learn and try to discover new things, you're going to come up with failure, because research in science is really about trying to do something, and usually we fail. We have challenges. And so we have to be flexible to change direction when we fail so that we go in a different path that might be more successful. And most importantly, don't give up. Just because you failed many times, that doesn't mean that you can't get to the end product. Don't give up. And finally, we have one life. It's not a dress rehearsal. This is the real thing. So you better enjoy it. So enjoy life. Yeah, thank you.